Okay, welcome class. We are discussing in the previous class about the linear quadratic optimal control system. We are designing a linear quadratic regulator in which we consider our reference input to be 0. So, my all the states are returning to the origin, they are coming to the 0. So, just to review what we have done, we have considered a linear system as x dot t equal to a t x t plus b t u t, y t equal to c t x t, a b c are the function of time. This means we are considering the time varying system. So, for a linear time varying system, our objective is to obtain a control which will take the plant to non-zero state to 0 state and minimize the Pi. Pi is a quadratic objective function which will contain the x transpose T f, f T f, x T f, which is my terminal cost, plus half of x prime q x plus u prime r u. So, x q x represent my error, u r u, u prime r u will represent my control efforts. So, I am trying to minimize the terminal cost, the error, because my final destination is 0. So, any point will nothing but representing me the error. So, each state at any given instant representing the error, and u prime r u is nothing but my I am trying to minimize the control efforts. And this LQR problem we solve using the Hamiltonian approach. So, first we represent a Hamiltonian which is nothing but my half of x prime q x plus u prime r u plus lambda prime a x plus b u. With this, my first condition is del h by del u equal to 0, which is giving me r inverse b prime lambda, and then I will have the state and the co-state equation which giving me the Hamiltonian system representing as x dot t equal to a t, e t is b r inverse b prime q minus a prime x and lambda. So, basically if you will see, this Hamiltonian system is giving me the two equation. One is I am representing my x dot t in terms of the a t x t, and another term is my e t is b r inverse b prime t, r is also the function of time, into lambda t. So, this is my first equation, a t x t minus e t lambda t, where e is b r inverse b prime, and my co-state equation is x t as minus q t x t minus a transpose t lambda t. So, I have the state equation as well as my co-state equation. If I will represent this system, so this is if this is my x t integral. So, this will be my x dot of t so a t x t plus Bt, and this is my nothing but Ut. This RT we are considering to be 0. So, this is my state equation. Because R inverse B prime lambda, this is nothing but my Ut. So, I am writing the first equation as x dot t equal to ATXT plus BT UT. If I will see the second equation, xt is multiplied with Qt So, what I am getting? I am getting lambda t, sorry, lambda dot t as Qt xt with negative sign. So, I consider my negative sign to be here. Integral, I got the lambda t multiplied with A transpose t So, here this is my lambda dot t is Qt xt plus lambda t A transpose t. Lambda t is multiplied with R inverse B transpose R inverse T B transpose T to get my U. So, I am taking negative sign with this. So, this is minus R inverse B prime multiplied with this. So, this block diagram completely represent my state and the co-state equation, and if you will see this upper portion is representing my state equation, while the lower portion, if you will see, this part is nothing but my co-state equation or say system, anything we can call. So, what actually for a given plant we have to write an algorithm to find out the value of R inverse B prime lambda. This we are trying to determine, and these are determined with, like in my system I am given with the xt0 and what is given here for lambda t. If you recall in the previous class, if we will apply our terminal conditions, so we got lambda tf equal to f of tf x of tf. So, with respect to this, so this is at this, normally my terminal point lambda tf is defined as, sorry, f of tf x of tf. xtf is my terminal endpoint condition, which is I have considered I have to transfer my all state to origin, because tf is finite. In a finite time we want to transfer our initial state to any 0 state. So, such kind of a regulator is nothing but my finite time LQR. So, this is nothing but my finite time LQR system is. The process to solve this problem is, we normally assume our lambda t as a matrix PT and xt, and this, as we said before, we get the intuition to consider lambda t as PT xt from my terminal condition, because this condition giving me f of Tf x of Tf. F of Tf is my terminal cost, and the nature of the f of Tf is, it is symmetric and positive semi definite. So, naturally my P of Tf, if I will consider lambda t as Pt xt as we are considering, so at the terminal point my lambda Tf is Ptf x of Tf. So, this give me nothing but Ptf equal to f of Tf. As f of Tf is a symmetric positive definite matrix, so P will also be the symmetric. It will be positive semi definite or positive definite, that we will discuss later on, but we select Ptf as a symmetric positive definite matrix. It is a symmetric because of the symmetry of my f. So, this P we will select as symmetric positive definite matrix. So, if I know P, I can directly implement my closed loop control as minus R inverse B prime Pt xt, and if we will just differentiate, and in the previous class we have seen, we are land up with this matrix differential Riccati equation, and by solving this equation subjected to Ptf equal to Ftf, we can find out the Pt, and if we can place the Pt here, we can have the closed loop feedback control. This means, if in this, because here all calculations we have to make it a closed loop. So, if I will modify this, now directly I am taking the feedback I have the to find out the Pt, and this we can find out offline. So, this Pt can be determined with the condition Ptf equal to f of Tf, and if I know the Pt, I can have my R inverse B transpose Pt, if I will, and can directly give as my ut. So, in a feedback case, this is nothing but my optimal state feedback controller. So, by utilizing by solving my matrix differential Riccati equation, by getting the value of the P, which I can solve offline, with this value of the Pt, if I will implement here, so this is nothing but my optimal state feedback controller, and the overall problem is my finite time linear quadratic regulator problem. So, in this way we can solve this problem simply by solving this matrix Riccati equation. So, we can write the algorithmic steps required to solve a finite time regulator problem. So, to get the optimal control using the finite time regulator problem, for the finite time regulator problem my algorithmic steps will be, first one I have to solve the matrix differential Riccati equation. What we will get? By this we will get the PT. So, for a PT is known, if PT is known, then I can find out then determine the control law. And what is my control law? My optimal control law will be minus R inverse B transpose PT into x of t, and this I can simply write my KT xt. So, my control law is KT xt. So, we can determine the KT if we know the value of the PT. So, my optimal control law will be ut equal to minus KT xt. My third step is solve for the optimal trajectory. So, what is the optimal trajectory? My system is xt x dot t equal to at xt plus bt ut. As if I will use u to be the optimal, so my trajectory I can say will be the optimal. So, u star t, if I will take this is nothing but at minus kt, sorry, this is at minus bt, and I am replacing ut by minus kt xt. So, negative sign I have taken here, bt kt xt. So, this at minus bt kt is my new This is my closed loop system matrix. So, whatever be the state of the AT, we will show later on. My closed loop system matrix if will be a stable matrix. If if we are able to find out the value of the PT such that UT can be determined. So, by simple solution of the PT, I can develop a complete state feedback control law to control my system. As we have seen in the previous lecture, for a first order system we can easily solve manually my Riccati equation, but in the another example we have seen, if my system is of the second order, then I will get 3 non-linear differential equations, and these 3 non-linear differential equation has to be solved with the final condition given as my PTF equal to f of TF. This is my f of TF, this is my P of TF. So, I know P11, P22, P12, these 3 parameter I have to find. So, for a total number of the equations, if we will see for matrix DRE, as PT is symmetric, so the total number of equations will be n into n plus 1 by 2. So, for a second order system I will have the 3 equation, and as the order of the system increases, these number of the equations will increase. Now, question here is how to solve these equations. These equations can be solved using any numerical technique like your Runge-Kutta Euler approach. Utilizing this we can solve this equation, but to solve them manually is not an easy task. So, any differential equation solution technique we can adopt to solve these equations. So, next we will see some salient feature of our Riccati equation as well as the regulator system. So, Riccati coefficient matrix is a time varying matrix which depends on the matrix AT, BT, Q, R and F, but PT does not depend on the initial state xt0. So, this means whatever be my state, if I know my system matrix like my AB matrix, Q and R matrix and the terminal cost matrix F. So, whatever be the initial condition of my system, I can develop my state regulator to drive this state to the origin, because I have to shift my I have to transfer my all the initial state to my final state, which we are taking near the 0 as we have seen before. So, the second feature is my PT should be symmetric, as we have discussed. This is symmetric because f of t PTF equal to f of TF, and f of TF is a symmetric matrix. So, PT will also be the symmetric matrix. Because PT is symmetric, so my Riccati equation, which is P dot, must have n into n plus 1 by 2 equations to get all the parameters of my P matrix. As we have seen for a second order case, my P is P11, P12, P12, P22. So, total number of the Riccati equations will be n into n plus 1 by 2. And these are the first order non-linear time varying ordinary differential equation, and any differential equation solution algorithm we can utilize to solve this equation, like we have said, Rangakutta Euler methods can be used to solve these differential equations. UT is the optimal control, U star T is minimum if the control weighted matrix is positive definite. So, it is minimum if it is positive definite, RT is positive definite, and maximum if it is negative definite. So, we will discuss in detail in the sufficient condition why this condition is there. So, for RT, what actually is the RT? So, if you will recall, we have defined the H as half of x prime t q t x t plus u prime r u plus lambda transpose A t x t plus B t u t, and for optimal control we have the condition del H by del u to be 0. And what was our condition if we are solving this? This was R t u t plus B transpose lambda t equals to 0. So, if I have to find out the u t, I need to be R to be inverted, R inverse t, B transpose t, lambda t. So, R to be inverted, this means R should be positive definite. So, R should be positive definite. So, my R should be positive definite, and later we will show if R is positive definite, then it will nothing but satisfy the condition of minima, which is my sufficient condition, which in the later part of our discussion we will prove this. So, after implementing, like we have seen, my closed loop system will be nothing but A transpose minus B R inverse B prime P t into x t. So, this B t R inverse B prime P, this is showing nothing but my k t. So, this is A t minus B t k t x t. So, this is my closed loop matrix, and we will also show that this matrix nothing but give me a stable closed loop system. Next point is the controllability. So, in a finite time regulator, do we really require my system to be controllable? So, the answer for this is no, because in a finite time, if I will solve my system, so for a finite time I always get my all values to be the finite values, whether it is the state or control. So, this means till my time is finite, my all other variable, all the states which I am finding, their value will also be the finite. So, if I will have the finite values, this means I am satisfying my bounded input, bounded output condition. So, whether my system is controllable or not, I am able to find out the some numeric value for the given states. Sorry, I can find out the some numerical value for my all the states. So, for a finite time regulator particularly, it is not required my system to be the controllable system, but in the later part as my TF will approach to infinity, then to get the solution my system must be a controllable system. Next is the stability of the closed loop system as my another feature. As we said, we will prove here that my closed loop system is a stable system. So, this lecture I will stop here, and in the next lecture we will prove that my closed loop system is a stable system. Thank you very much.